3i contains an awful lot of material between scatter plots, correlation, and regression, much more than what one of these usually contains. And if you look at the Newton notes, they're really, really long. They're 48 slides. Usually for one section, they're maybe 10 to 12, I would say. So much longer than normal. And there are things in there that we don't really need in order to answer the homework questions. So there are a few things in there that I am going to leave out. But there is actually a lot of material in there that we do need. And for some of the homework questions, I threw in a lot of background and context in these notes, specifically for the ones that involve the table, where you have to use the table to get the critical values. That, I didn't want it to feel like it was just floating there, and that's a whole can of worms because that's hypothesis testing. And if I did that fully, it would be really, really, really long. So I tried to cut that down as best I could while still trying to get some sort of context in there. I figured even for those questions, if you just see the context once, I think it makes that feel easier. Because at least for me, if it was just kind of floating there like, you know, here's this thing to do, but it's not entirely clear what it's for, that to me, that makes it harder. So that's why I threw that stuff in there. If you don't want that background stuff, you can just skip those parts and that's fine. But if that's a thing that does help you, that's why I put it there. I figured I'm probably not the only person that has that sort of thought process. So first things first, scatter plots, they're just graphs, but specifically they're graphs where you have two variables measured on the same set of individuals, two quantitative variables. So then you put one of them on the x-axis, one of them on the y-axis, and then when you plot points, it's like plotting ordered pairs, right? So just like in algebra, you know, plot the point 2, 5, you go 2 to the right and 5 up. It's that same sort of idea. And if there is a cause and effect relationship or a sort of hypothesized cause and effect relationship, like if you think there's one, then the cause variable, so your input, that goes on the x-axis, and then your effect variable, the output, that goes on the y-axis. So like here with this example, you would think if there's going to be a cause and effect relationship, it's going to be that the cause is spending more money on advertising, and then you would see the effect on the revenue, right? You'd think that's the way it works. If you spend more money on advertising, you're more aggressive on, you know, buying up airtime for commercials and things, then maybe you're going to see more revenue. So that's kind of the idea here with the chain of furniture stores. And if we were going to graph the scatter plot, which isn't a very big one, it's only going to have 4 points, because each month here basically is an individual where it's got two measurements. It's got an advertising measurement and then a revenue measurement. So we're going to have to plot some points. So, oops. Started to write the word plot, and I meant to start writing the word point. Confusing myself here. So points to plot. So there should be 4 of them. So we're going to have to plot the points 2, 7 for July, then 1, 3 for August, then 3, 8 for September, and then 4, 10 for October. So 2, 7, that's going to be 2 over and 7 up. It looks like that's there. Then 1, 3, 1 over, 3 up is there. Then 3, 8 is there. And then 4, 10 is right there. So there's our scatter plot. So constructing one, if you had to do it by hand, it's just like plotting points in a regular old XY plane, pretty much. But I mean, that kind of makes sense, right? The XY plane is 2-dimensional. This is 2-dimensional because we've got the 2 variables. So then it just kind of ends up being the same sort of concept. So actually making a scatter plot isn't anything too crazy. But then, well, what do you get when you have one, right? What's the point? Why do you need the graph? Why can't you just have the table? Because some things are easier to see when you have the graph. So that's the next thing. It's easier to see trends, patterns, deviations. Deviations basically would translate to the word outliers. That's a thing that'll come up a lot in this section, where outliers are basically just points that are outside the overall pattern, right? So they are deviations. But if you're looking for patterns or trends, usually what you look for is just, is there a general thing that happens, like as one variable gets bigger, does the other one get bigger? Or as one variable gets bigger, does the other one get smaller? So things like that, that's what you want to look for as far as a pattern or a trend goes. And that's basically what's right here in these 2 bullet points. So a positive association, that's where as one variable gets bigger, the other one gets bigger. Or I guess to say it the better way, larger values of one variable correspond to larger values of the other one. And so that would mean that if you look at the scatter plot from left to right, then the point should kind of trend upward. So it's like what would happen if you had a line with a positive slope, right? If you have a positive slope, then as you go left to right, it goes upward. Then you could also look at this as like, well, if you had a scatter plot there and you drew in a best fit line, it would be one that had a positive slope. And the graph where it says positive association, you can tell, right? If you drew in a best fit line, I'll try to do this here, it's going to go like right through all these points. Right? It's basically just going to do this. And yeah, that line has a positive slope. Right? And then a negative association, that's the other way around, where there as one variable gets bigger, the other one gets smaller. Or to say it a better way, large values of one variable correspond to small values of the other one. And that's when you get a negative association. And if I drew in a best fit line here, I guess it would kind of go like this. Right, and that's probably a little high. I probably should have drawn that a little bit lower because I've got way too many points underneath the line. But it's that idea, right? It's going to be going downward left to right, just like any line in algebra with a negative slope, right? That's what they do. You got a line with a negative slope. As you go left to right, it goes downward. So that's the idea. And then what if you can't see anything, right? Because they don't have to be this nice. Because, I mean, let's face it, these 2 pictures that are on the screen right now, the one on the left looks really, really nice. Like, if you're looking for a trend, you look at that thing, you think, okay, yeah, it's right there. And even the one on the right, they're more spread out, but you can still see it pretty clearly. But what if you have something like this, where it's just a bunch of points just kind of strewn about? You can have no association. So like it says up here, no discernible pattern. That's exactly what we've got here. Another way to look at no discernible pattern would be if you kind of have this mentality of trying to mentally put in a best fit line. If you look at that one, where does the best fit line go? That is not clear at all where that goes, right? It's just a jumble of points. And if you can't see where it goes, that's fine. That's the point. That's the idea. You're not supposed to be able to see it. So that's what no association looks like. You look at it and it's just a bunch of points just thrown about everywhere, and there's not really a pattern at all. So that's a possibility. There's less that you can do with that, but it does happen. So got to bring it up, right? All right, next thing is outliers. So an outlier is a point that deviates from the overall pattern, and let me use a different color and one that's not one of the ones I have in these pictures. So not blue and not red. All right, so there is an outlier up there, that red point. So right there. That's an outlier because you got your overall pattern over here, right? So there's the overall pattern. So if you had an X value like this red dot, so it looks like it's 30. So even though the conversion of the PDF looks like it's distorting the axes a little bit, that point looks like it's about 30, 40. Right? So I would guess that's about what that is, roughly. So for an X value of 30, it should be like over here. Like it should be like, it should follow this pattern. And maybe like if you had something like this, you know, like that wouldn't be an outlier. That would kind of fit with what's going on with these black points. But having a Y value that large, that's really weird. The other way you can look at it is for having a Y value that large, then maybe it should be back here and have an X value of like 5, right? So that's way outside the overall pattern, so that's an outlier. So it's the same overall pattern. It's actually the same graph. I just basically cut and pasted the red dot. But that's another outlier in this one. And it looks like the coordinates are about 520. So 520 is that point. And yeah, if the overall pattern is the black dots, that red dot, it's, I guess for an X value then of 5, then this is way too low. It should be like up toward the upper left corner where the dots are. Or you could say, for a Y value of 20, it should be way over to the right compared to where it is right now. Then there's this third one, and it says it inside this box, that this one right here, this blue dot down here, this is not an outlier. And the reason is because that even though it's still kind of separated from these other points, from the black points, it still fits the overall pattern, right? Like if you had a best fit line that you drew through all the black points, it would be pretty close to that blue one, right? So if you look at the two up top, those, if you drew in a best fit line through the black points, those red ones are nowhere near that best fit line. But then down here, that blue one, yeah, that still fits in. And there was actually something I was looking for and I couldn't find it. I had this data set about Archaeopteryx bones, like the prehistoric bird-like creature. And there were a bunch of them that were all clustered together. And then there's one where the X and Y values are both really small. And it's like, like the two bones are both really little, right? And so what does that mean? Well, that means that's a baby, right? Like instead of being an adult where the bones were all kind of clustered together, it was like there were like 4 or 5 adults and then one baby. But the baby data point fit in with the rest of the pattern. It was just that both measurements were smaller. And that's kind of what this one's like. This is fitting in the overall pattern. It's just that it's kind of separated from all these other ones, but that's okay. Right? It still fits the overall pattern. It would still be close to a best fit line if you drew one in. So that's actually not an outlier. That's kind of the case that you have to watch out for, right? Because outliers tend to be kind of spaced out from the rest of the points, but they also have to be outside the pattern. And that blue one's not. So that is the one thing you got to kind of watch out for, because there are a bunch of questions in the homework that are asking about outliers. And if you get one like that, that's actually okay. That's not an outlier. All right, next thing is correlation. So what correlation is for is actually to compute strength, because you can't really figure out the strength of a linear association by eyeballing the graph, because how strong it looks is kind of based on how the axes are calibrated. Because if the axes are kind of calibrated weird, then something that really isn't that linear, you can make it look linear, and vice versa. Something that's actually a pretty good linear relationship, if one of the axes is stretched out, might not really look it. So the correlation coefficient is really a way to quantify strength. And like it says here, you get strength and direction. It's sort of like you get the direction for free, because you can probably figure that out just from looking at the scatter plot, right? Like if you have a positive or negative association, you can tell by looking at it. You don't really need the correlation for that. Although I guess if you didn't have the scatter plot, but you had the correlation, then you would know, okay, well then this is kind of generally what the scatter plot looks like. You got a positive correlation, points must be trending upward, left to right, that kind of thing. So the correlation does measure the strength and direction of the linear association between two variables. Linear is important because if you have a non-linear shape, then the correlation might end up being really weak. Like if you have something that kind of looks like a sine wave, you'll get a correlation that's close to 0, even if there's a clear pattern there. Notation, the sample correlation is R, and the population correlation is a lowercase Greek letter rho. So the thing that kind of looks like a P, that's what that is. And we will need that actually in a little bit. Computing the correlation from scratch, if you want to do it, have a good time. I would not do that by hand. If you really, really want to have that experience, I can't stop you. But to me, this is a thing that I don't really want a part of right here. And that's one of those things where I think, that's what calculators and applets are for. Not that the computation is hard. It's not hard exactly. It's just that there are a lot of little pieces that you have to do. So it takes a long time. That's definitely true. Um, but I actually need this formula as a prop for a thing that I have to bring up later. That's kind of the reason that it's in there. But you could compute it by hand if you really, really wanted. I can't stop you. I'm assuming no one will take me up on that, and I do not blame you whatsoever. All right, so the properties of the correlation, the way that computation is set up, the values are going to be between -1 and 1. It is possible to get values of exactly 1 or exactly -1, but it's not realistic. Like not with a real life data set, because in order to get 1 or -1, like those exact numbers, you have to have scatter plots that are perfectly linear, like where all the points are just lined up perfectly. In real life, you don't get things that look like that. And even to get exactly 0, you would need like a perfect geometric shape. Like if you had a perfect circle, you would get a correlation of 0. Or like a perfect square. Not really going to get those either. So you tend to get values that are close to that if you have something that's really linear, but not exactly -1 or not exactly +1. And if you have something really weak, you don't get exactly 0. Maybe you'll get like 0.016 or something, right? You get something really close to 0, but you don't get exactly 0. So the sign matches the direction of association. So this is where you kind of get the direction for free. Where if you have a positive association, you get a positive correlation that goes with that. Negative association, you get a negative correlation that goes with that. Strength, this is kind of interesting. The farther away from 0 you are, that indicates a stronger correlation. That's pretty straightforward for the positive numbers, but it's easy to get the negatives backwards. So farther away from 0 is stronger. So what that would mean would be something like if you have a correlation of, let's say, -0.87, that is stronger than, I don't know, let's say r equals -0.41. Since -0.87 is farther away from 0. Also, and this is the one that really tends to throw people off, r equals -0.87 is stronger than, and let me just come up with a positive one that's kind of strong, like 0.73, right? Because -0.87 is farther away from 0 than positive 0.73 is. So that means that the -0.87 is a stronger correlation. So that's the way to kind of interpret whatever number you get for the correlation is farther away from 0 equals stronger, and farther away in either direction. Then the other points here, the correlation has no units, so it doesn't depend on the units of measurement. That's nice, because that means that if you have things that are lengths, let's say, then if you use metric or if you use imperial measure, you're going to get the exact same correlation. That's good, right? Because really those lengths are actually the same amount, right? They're just being calibrated differently. So it's nice that you end up with the same correlation. And then the order of the variables doesn't matter for the correlation. So this is why even if you don't really have a cause and effect relationship between the variables, you could still figure the correlation out. And actually, if you look at the formula, like if you go up here, the x and y parts are multiplied. So multiplication commutes, right? You can flip the order. 5 times 2 and 2 times 5 are both 10, right? So the x part times the y part, you could just flip the order and say y part times x part, and you would get the exact same thing. So that's actually helpful. That flexibility is there in the cases for when we don't have a cause and effect relationship where it's just two variables. All right, then I made some pictures. So a strong positive, and you can actually see the correlation, right? Like it's down there in the corner. That's what this is, right? So that right there, that's R. So the red numbers, that's what those are. They're the correlations. So I did this in a program that's called R, and you can make it print the correlation in the corner. So I made it do that. And I think it just, like, it put that one in the upper right so that way it wasn't in the way. because if this one, if it was in the lower right, it would be on top of a bunch of points. But a strong positive correlation, and you can see it 0.9387, but also just looking at this, you go, yeah, that's positive, pretty obviously, right? Points are shifting upward left to right. The strong negative, you look at the graph, the scatter plot, you go, yeah, that looks negative. They're going downward from left to right. And you can see the correlation up there in the corner, the negative 0.9249. Then, let's see, weak positive. So you can look at this and you go, yeah, if you were going to draw in a best fit line, it probably kind of goes like that, sort of. And there are some points that are pretty far away from it, right? It's not like the points are tightly wrapped around that line in a nice linear fashion, right? That's not much of a linear shape there, so the correlation ends up being kind of weak. It's 0.2985. This one is a weak negative. I guess if you were going to draw in a best fit line, it probably goes kind of like this. Where then you got a lot of points that aren't really close to it, right? I mean, that's really not a linear shape in that scatter plot either. And then there's one more. It's actually on the next page. Practically no correlation. It's negative 0.0574. And if you look at that one, you think, yeah, I don't even know where to begin drawing in the best fit line. But that's kind of the point, right? If you have no correlation. Or zero correlation or close to zero. That's what it should look like. Backtracking a little bit, that note at the bottom, the concept of strong and weak are relative. Like it depends on what your variables are, pretty much. So it depends on the context. There are situations where maybe, like if it's financial modeling, maybe a 0.2 is really good. And like if everybody else is getting like a 0.08, 0.09, and then you come up with something where you got a 0.2, relatively speaking, that's a lot stronger, and then I know there was, and I used to have this, I don't know what happened to it. There was this biology thing where there was some subfield where in order to get a better model than the ones that already existed, you needed a stronger correlation than 0.94. And you think that's a pretty high bar to clear. But yeah, right? So in that context, you'd say, well, you get like a 0.91, that's not strong enough, right? That's not strong enough to get your findings published because other models are better than that. So strong and weak are relative, but the idea of stronger and weaker, like, maybe if you had an outlier and you took it out, and then the correlation went from 0.7 to 0.8, then you would go, oh, it got stronger when the outlier was taken out. So the idea of farther away from zero being stronger and closer to zero being weaker, that's an important point, but there's no like absolute idea of, everything above 0.6 is strong or anything like that. That doesn't really work. It's so context dependent that you can't really, like it would be nice if that existed, right? If there were like these thresholds where you go anything above this is strong, no matter what the variables are, but it doesn't really work that well to try to say things like that. Let's see. And here's the thing with the sine wave. If your correlation is close to zero, that means that the two variables have a weak or non-existent linear association. They could still have some kind of nonlinear association though. So average temperature versus month, this is just going to kind of repeat year after year, right? It's going to go up, then it's going to go down, and then up, then down. And you would get kind of a sine wave type shape where there would be a clear pattern there, but also one that's not linear. And if you try to draw a best fit line through the sine wave, it just goes right through the middle of it. And yeah, that's going to end up being a correlation that's pretty close to zero. So that I just wanted to kind of throw in because that's a way that you can have that happen. It's possible to have a nonlinear pattern where the correlation comes out as really weak just because the correlation really just measures the strength of a linear association. All right, next, and this is where I threw in a lot of backstory for the hypothesis testing. So there were homework problems that have this table. And I've actually got it in here somewhere. Let me see if I can find it. Shouldn't be that hard. There's the table. This table that's here inside the box, that shows up in a bunch of homework problems. And it really just says in the problem, use the table to determine if the correlation is significant. And that's really about what it says. What that really is that that's a hypothesis test. There's the beginning. Okay. And so what a hypothesis test is, so just like how before we had confidence intervals come up, even though it wasn't really called that, it was called like the range of percentages. This is kind of similar, where it doesn't really say hypothesis test anywhere, but that's what this is. Like when you're using that table, that's what you're doing. So what a hypothesis test is, it's where you have some claim about a population parameter. In this case, it'll be a population correlation. But you could do it for other stuff. You could do it for a proportion if you wanted. You could do it for a mean. So you can do it for other things. But you try to assess a claim about a parameter using sample data. And really what you end up with is competing hypotheses where they're called the null and alternative. The null hypothesis, and if you think about null being like zero, where that's a statement of no change, no effect, no difference, right? Zero change, zero effect, zero difference. Null, zero, right? And the notation is an H for hypothesis with a subscripted 0 for null, which is usually pronounced as H null or H sub 0. And it typically has an equal sign in it, and you can see it down under where it says hypothesis test for a correlation, right? So like here's your null right here. It's that first one, right? There's the H sub 0 if you look over to the left, and then it says population correlation equals 0. So there it's got an equal sign in it. Then the other hypothesis is the alternative, and it's, at least verbally, the opposite. So some effect, some difference, or some change, right? Some effect instead of no effect. And so when you're doing a hypothesis test, that's the one that you look for evidence of. So basically what you do is you have your sample data, and you try to see if what you can pull out of your sample data. So like in a test for correlation, you'd be looking at your sample correlation, right? Like you're looking at the measure you're interested in, just the sample-based version of it. And then you want to see like, well, is this going to give us evidence to where we can throw the null hypothesis out and say that it looks like the alternative is right? And so the alternative, its notation, it's an H for hypothesis with a subscripted A for alternative. Older books tend to use an H1, like older statistics books. Also, like that's more common if you look in like biology stuff. So if you happen to look anything up online and you're looking at some biology thing, then it might have an H1. It seems to be more common there. Kind of like how in physics they call the normal distribution the Gaussian distribution. In biology you tend to see H1 instead of HA, right? It's just a notational preference thing. But then this one underneath is our alternative. And you can tell because it says H sub A over on the left, but it also has an inequality. So you can have one-sided inequalities when you have a less than or a greater than. We're not going to bother with it. It doesn't show up in the homework, and it's much more common, especially for a test of correlation. I've never seen anything other than this. You could have a one-sided test if you really wanted, but I mean, the defaults for any kind of software are to do it like this, where the null is that the correlation is 0, the alternative is that the correlation is non-zero, because what's a zero correlation? If you have a correlation of 0, that means that there's no linear association between your two variables. So between x and y, whatever they are. And then a non-zero correlation would be some kind of linear association. So like this is the first step in any kind of analysis of the correlation, right? First, you want to see, is there anything here? Because if you don't have enough evidence to conclude that the correlation is non-zero, then you're like, well, we just don't really have anything here, right? It's nothing worth pursuing at this point because there's no evidence of a linear relationship. So then you wouldn't take the next step and have the linear model or anything like that, because if there's no evidence of a linear relationship, then what would the linear model be for, right? You wouldn't go there, right? You'd be doing extra work that kind of just goes down a dead end. So that would be the first step, and that's why it's thrown in here in the homework. It's is there any kind of linear association? That's the thing that we're going to be looking for when we do this. So specifically, this is the thing that we are going to have, even though it doesn't explicitly show up in those homework problems. It's the thing that you're actually doing. All right, so then how do you figure out if you have a significant result? And when you have a significant result, this is when, so let me just circle this and kind of point this out. When this happens, when you have a significant result, this will be when you reject the null and conclude that the alternative is likely to be true. So in a way, that's kind of the thing that you want, right? Because if it looks like there's a linear association, then you can say, yes, now we can have a linear model and we can use it for predicting things, right? So in a way, it is kind of the one that you want. But how can you do it, or how can you figure out if you have a significant result? Well, first, you have to have something called a significance level specified. And the most common significance level is 0.05. So kind of like how the most common confidence level when you're going to construct a confidence interval is 95%. So like the idea of how 95 plus 5 is 100, or 0.95 plus 0.05 is 1. So those two things do relate to each other. There is actually a way to do a hypothesis test using a confidence interval, but we're not really going to get into that. But there is a way that you can do it. Like if you take a statistics course that would get into inference, then you would do it. You would definitely do it. But our table is not really equipped for that. So it's never specified in this section, but that is the confidence or the significance level that's used is the 0.05. And it's so prevalent that when it's not specified, then you would just assume that it's 0.05. Like that's the way that it's done conventionally. If nobody tells you what the significance level is, you just assume that it's 0.05 because that is by far the most common one that's used. If someone was going to use something else, they would tell you. So that's what we're going to do when we get there. We're just going to assume that it's 0.05. And there are a couple of ways that you can do it. You can use p-values, which is what most software would be programmed to give you. Like if you used Excel and you turn the data analysis tab on, it's going to give you p-values. Because for software, it's easier for it to just spit out the p-value. But p-values and rejection regions are equivalent. So like if you reject the null with one of those, you're going to reject the null with the other one. And if you don't reject the null with one of those, you're not going to reject the null with the other one. I suppose that would also be true. The p-value, I'm going to run through this really quick. This does not actually show up in the homework, so if you want to skip this part, go right ahead. But this is kind of just a general knowledge thing, but I thought this looked really incomplete without this, so I wrote it up. So what the p-value is, it's a probability that you can compute, and it's the probability of getting a sample measure, so like a sample correlation, at least as extreme as the one that we got under the assumption that the null hypothesis is true. So like assuming that the population correlation is 0, then what's the chance that we got a sample correlation of at least whatever? So like if we had a sample correlation of like 0.7, what's the chance that we got a sample correlation of 0.7 or greater, or negative 0.7 or lower, under the assumption that rho is really 0? So that's the thing that you would figure out, and you have to use a reference distribution to do it. But using software to do it, it's not that bad. If you try to do it by hand, it would be a little rough, admittedly. I've never done it all the way through by hand, so I couldn't tell you. You have to use kind of an obscure integration move from Calc 2, and it's kind of long, but you can do it. But that's one of those things where that's what software is for. And then basically the way it works is if the p-value ends up being a number that's less than your significance level, then that's when you would say, oh, we have a statistically significant result, so we can reject the null and conclude that it looks like the alternative's right. If the p-value is not less than the significance level, then you can't reject the null, and that's about all you can say. So then I just made up some numbers, and I said, so let's just suppose in a test for the correlation, we got a sample correlation of negative 0.63. The p-value, if that's the chance of getting something at least as extreme as negative 0.63, under the assumption that the null is true, then it would be the chance or the probability of getting a sample correlation either less than negative 0.63 or greater than positive 0.63. So at least 0.63 away from zero in either direction, under the assumption that the null is true, which would be that rho, the population correlation, is zero. Okay, and then I just made up a couple of p-values just to show what the different conclusions would be. So if you got one that was less than alpha, so less than your significance level of 0.05, so like the 0.029, that's what that one is, then you would get a statistically significant result. So you're going to reject the null, conclude that the alternative is likely correct. So you would conclude that rho is non-zero. So it looks like the population correlation is non-zero, which means that it looks like there's a linear association between the two variables, right? So then that's the one that you kind of want to get, right? Otherwise, if the p-value is too big, so if it's not less than 0.05, like if it's 0.086, like in this last bullet point, then you would say that you don't have a statistically significant result, and that means that you can't reject the null. However, that's about as far as you can go. You can't then extend that to saying that you accept that the null is true. That statement's too strong. Like from a logical perspective, that's just like a bridge too far, so to speak. And it's kind of like in a trial, where it's not that the possible verdicts are guilty and innocent, it's that they're guilty and not guilty. So it's kind of like that if your p-value isn't less than 0.5, so if it's too big, like the 0.086, then that's when you just don't have enough evidence to convict the defendant. It's like that, right? So you'd say that they're not guilty. Just like here, it's like you don't have enough evidence to say that it looks like the null is wrong. So you say, well, we don't have enough evidence to throw the null hypothesis out. We don't have enough evidence to reject it. And that's as far as you can go. All right, so that's how you would do it with a p-value. The conclusions are kind of similar for a rejection region, but the way that you get there looks a little bit different. So rejection regions. So this is the one that shows up. And this is another one of those things where the phrase rejection region doesn't actually show up in the homework, but it's what you're actually doing. So the way that the rejection region works is you take your significance level, so your 0.05, and then under the assumption that the null is true, you would set up your rejection region so that the probability of getting a value in the rejection region is equal to the significance level. That's easier than it sounds, especially when you have a table. If you didn't have the table, it would be really hard. Well, or any software. I guess with software, it's not too bad either. You could do it without the table if you had to. All right, so on the Newton homework, all the correlation tests have the two-sided alternative. They're set up for that. So that's the not equal to in the alternative rather than a greater than or a less than. And so that means you have to consider both directions, right? Not equal to could be less than or it could be greater than, so you have to consider both. And that's what two-sided alternative is about, like that phrase. That's the not equal to, and that just means you have to consider both directions because not equal to could be less than or it could be greater than, right? That's two different ways it could happen, two sides in the picture. So there's like this picture down here. So notice how there's the red part in the left and the red part in the right. That's the rejection region. And so you have to consider both. So like the left would be a less than and the right would be a greater than. All right, so going back up here, what you would have to use in order to, if you had to generate the rejection region yourself, you have to use something called a t-distribution, which I put the properties of that on the next page. It looks like a normal distribution because actually in this picture down here, that's a picture of a t-distribution. And if you're looking at that and going, looks like the same thing, that's kind of the idea. They do look like the same thing. And the part that's different, you wouldn't really be able to see in that picture very well. The part that's different is that the tails are thicker. That's the only difference. It's like a standard normal because it's centered at 0, right? Just like a standard normal is, but with adjustable tails. And basically it's because there's extra variability that you have to contend with. So that's why you need the tails to be thicker. And I guess if the tails are thicker, then the center of the curve, the peak, has to be shorter because the area under the curve always has to be 1, right? So bigger tails, you got to shrink the peak down to preserve that. But the big thing is just that it looks like a standard normal, but the tails are thicker. If that's the takeaway, that's enough, I think. And then graphically, your significance level should be equal to the area under the curve in the rejection region. So if alpha is 0.05, right, so our significance level is going to be alpha equals 0.05, then look at the two tails. So these numbers that are kind of hovering in the tails, where there's the 0.025 there and the 0.025 up there in the right. So those are both alpha over 2, right? Because they're 0.05 divided by 2. That's the idea. That's how you would form the rejection region when you have the two-sided alternative. You take your alpha and you split it in half, and you put half in each tail. And the reason you can split it in half is because, just like a standard normal, a t-distribution is symmetric. So when you split it into the two tails, they're going to be the exact same size just by symmetry. So that's how this all gets put together. So in that picture, so you can see like the red parts are the rejection region. So like it says in that first bullet point, the cutoffs are called critical values. This is an important term because it shows up in the table that shows up in the homework. If I go down to where the table is for a second, which is here, where it says CV, CV stands for critical value. So that's right there in that table. So that's an important thing. This picture is a little bit different than how our table is set up. And you can tell because if you're thinking, hold on a second, the correlation is supposed to be between -1 and 1. What's this business with these cutoffs being like a little over 2 and a little under -2, right? Wouldn't the correlation always be in the middle? This isn't actually set up to use the correlation directly. You would have to compute something called a test statistic, and the test statistic formula, it's right here as the last thing on this page. If you had the correlation, it's honestly not that hard. I mean, you got to feed it into your calculator, but it's not that bad. And if you have a calculator that can't do all that in one line, you do the denominator first, and it'll work out. Like it's not too bad. But the way that our table in the homework is set up is actually really nice because you don't have to compute this thing. But the way that would work, I guess, let me see if I can get all this on here at once. Okay, good. So we can still see the cutoffs in the picture. Like the -2.069 is the cutoff on that left tail, and the positive 2.069 is the cutoff on that right tail. So if that's the rejection region, then you're going to reject the null and have a statistically significant result if your test statistic is in there. So if it's either less than -2.069 or greater than positive 2.069, right? So that part right there. The other side of that is, what if your test statistic isn't in either of those tails? Well, then it's in the middle, right? If it's between -2.069 and positive 2.069, it's not in either of the red parts, it's in between them, and that's when you would not reject the null and you would not have a statistically significant result. So then the table that we have in our homework, so this is an important point right here, it's back solved for R. So instead of having to compute the test statistic and then compare that to the critical values that are there in the table, it's back solved for R, so you can just look at your sample correlation and compare that to the critical values in the table. So basically, it's if you took the formula that's at the end of the last page, so the thing up here with an arrow pointing to it, that's kind of in the upper right now, if you solved that for R, which looks like it's kind of a nightmare algebraically, it's not the greatest. It's not the worst thing in the world, but it's not the best. But if you did solve that for R, you would end up with that table that's in our homework. That's basically where it comes from. And that's nice that we don't have to compute the test statistic, right? That's some algebra that we just don't have to do. Okay, I'll take that deal any day of the week, right? So more stuff about t-distributions. Just to have a little bit more context with it. And I'm going to change colors just in case I need to. Maybe brown. That doesn't show up in those pictures. Okay. So we know that it looks like a standard normal. It's a bell shape, centered at 0, except it's got the thicker tails. Other than that, the t-distribution is characterized by something called degrees of freedom. And the degrees of freedom is different for different things. Oh, and by the way, I guess another thing that's worth mentioning with this picture up here, I didn't say it and I should have. So why is this set up for the test statistic when it would be easier if you could just do it using the sample correlation? It's because the t-distribution is not just used for correlation. It's also used for the mean and for anything that's mean related. So like if you did a test for like a difference of means, then like the difference between two different means, you would also use the t-distribution. So it has a bunch of different uses, and so there's kind of a generalized version where you use the test statistic because then that works for everything. That's why. And so the degrees of freedom actually is computed differently for different quantities, but for correlation, so this is a huge point here as far as using that table is concerned, the degrees of freedom is n minus 2. So where does that come from, like this concept of degrees of freedom? Basically, what you would start out with is that the degrees of freedom is equal to your sample size. However, if I scroll up for a second, I can actually show you where the minus 2 comes from. It's in, where is it? This is way up here. There. It's in that formula that's in the green box. So if you were going to grind out the sample correlation by hand, the reason that it's n minus 2 is because when you do a computation that involves every point in the data set, you lose a degree of freedom. And if you look at this, it has x bars and y bars. Each of those, because in order to compute x bar, you add up all the x values and divide by n, right? In order to get y bar, you add up all the y values and you divide by n. Both of those involve all of the data points. And so for each one, you lose a degree of freedom. That's why it's n minus 2. That's why I had to put this in here, even though we're never going to grind it out by hand. But that's why. I just wanted to have that reference when we got to the n minus 2, and I could kind of point at that. There is a proof that that's why it works. That proof is really long, but that's the gist of it. It's because there are those computations that involve the entire data set. And you've got 2 of them, so it's n minus 2. So that means that like if your sample size is 30, your degrees of freedom is going to be 28, right? Or if your sample size is 14, then your degrees of freedom is going to be 12. And then this idea of the smaller degrees of freedom, that's when you'd have a smaller sample size, where that would give you smaller degrees of freedom. Then you need really thick tails. So like if you look at the picture that's here on the right, I think this one's easier to see. The red one with the 5 degrees of freedom, notice how the tail, the red tail is above the blue tail on both sides. So that tail's got to be thicker because the degrees of freedom is smaller. But if the tail is thicker, then the peak has to be shorter because the area under the curve's always got to be 1 no matter what, right? So tails get bigger, peak gets shorter. And then for the blue one, where it's 40 degrees of freedom, the tails are thinner, right? Because the blue tail is underneath the red tail on both sides. But then the peak would be taller because, again, area under the curve always has to be 1. And then that last part, if your degrees of freedom just keeps increasing and increasing and increasing, eventually what you get looks like a standard normal. And that's the idea in the picture on the left. So like if you go from black to red to green to blue, like black to red, the green to green, the degrees of freedom is going up. And then blue is when it's standard normal. And so notice the blue, it's got the highest peak and it's got the lowest tail. So it's like eventually if your sample size keeps going up, which would make your degrees of freedom keep going up, you'd eventually get closer and closer and closer to the standard normal. And you'd get something where the difference would be negligible with a big enough sample size. All right, so now we can actually get to using the table. All right, so this is the exact table. I just did a screenshot of the one that's in the homework and blew it up so it was really big, but this is the exact same thing. So how do you use it? So for the data set that was on the first page, which had the advertising expenditure and revenue for 4 furniture stores, the correlation for those values, I went through and figured it out. It's 0.965. So then if we're going to use the table below to determine if R is significant or not, All right, so if we're going to use that table, then what we're going to have to do is first just figure out the degrees of freedom. But n is 4, right? We know that. So if n is 4, then that means that the degrees of freedom is n minus 2, which would then be 4 minus 2, which is 2. Right, so we want to be in the 2 degrees of freedom row. So then in the table, if the degrees of freedom is 2, then that means that the critical values, since that's what CV stands for, would be plus or minus 0.950. And you can draw the picture if you want. And actually, I think here, at least for the first example, it's probably a good idea. That's why I left all this space. So I'm just going to draw a bell curve here. And so then it's going to be centered at 0, right? And then we're going to have a negative 0.950 out there, and a positive 0.950 maybe about there. And then, since I can change colors here, I'm gonna. And I'll make the rejection regions red, just like they were in that other picture. All right, so that red part, I'm just gonna say RR for rejection region. So it comes in the 2 pieces like that. All right, so that's what the critical values tell you. It tells you anything past that in either direction. So bigger than positive 0.95 or less than negative 0.95 would be in the rejection region. Okay, well then our sample correlation, if I go back up here for a second, it's right here, right? It says sample correlation of 0.965. So where's that going to go in my picture? Well, it's bigger than 0.95 by a little bit, right? So it's up there in that tail, and that's where you're going to have the sample correlation of 0.965. All right, so it's in the tail, so it's in the rejection region. So we can say R is in the rejection region. So that would mean that if you think about it in terms of the hypothesis test, like with the null and alternative, that means that we should reject the null. So I'll just say we reject the null. The way that they phrase it in the homework is more like this. So I'm just going to change colors just so these things will kind of stick out from each other. But the way they would do it in the homework would be something like that R is significant. So the is significant, I suppose, is the important part there. Since it is not between the positive and negative critical values. Right? It's not between them because it's out in the right tail. But the answers on the homework tend to look like the one that's in brown. It's a multiple choice question. So like it is significant because it's not between them, or it's not significant because it's not between them, or it is significant because it is between them, right? Like you give 4 answers like that and you just have to pick the right one out. But they tend to be phrased like that thing that's in brown. All right, then there are a couple more of these. Let's see. So then data set with 17 values. The correlation is found to be 0.319. So then is that going to be significant or not? Well, let's see. If n is 17, then the degrees of freedom must be 15, right? So if n is 17, then the degrees of freedom is n minus 2. So that's 17 minus 2, which is 15. So then in the table, we need to go to where there are 15 degrees of freedom. And if you look at where that is, it looks like our critical values are plus or minus 0.482. Right? So that's what we've got now. Right? So now I guess I can circle the ones that we've been using. Right? So this one is number 1. Then this is what we've got for number 2. Right? Because we've got 15 degrees of freedom. All right. So then if we go back down here, so then from the table, we have that if the degrees of freedom is equal to 15, then that means that our critical value is plus or minus 0.482. And I think at this point you probably don't need the picture, but I'm going to draw one anyway because I have the space. All right, so let's see. Negative 0.482 and positive 0.482, and make them red again. All right, so then there's one part of the rejection region, and there on the left side is the other. And then where is our sample correlation? Well, it's 0.319, so it's bigger than 0, but it's less than 0.482, right? Like it's maybe about here. So it's not in the rejection region. So what we would end up with for an answer is, well, it's not going to be significant, or we would not reject the null, right? So R is not in the rejection region, which would mean that we do not reject the null, or the statistics book way of saying it, we fail to reject the null, right? Same concept. For whatever reason, every textbook writes it like that. But then to make it look like an answer that would show up in the homework, it would be something like that R is not significant since it is between the positive and negative critical values. All right, so it is not significant. It is between them, right? Okay, one more. Because the other one, this is kind of the tricky one. So now with 26 values, the correlation is negative 0.426. All right, so then if n is 26, then the degrees of freedom is going to be 24. Right, so the degrees of freedom is going to be n minus 2, which here is 26 minus 2, which is 24. But then, let's see, then if we go up to the table with 24 degrees of freedom, let's see, then we're going to be right here. So that's number 3, the 0.388. So we need positive and negative 0.388. All right, so then going back down here in the table, lost the ability to write for a second, got it back. All right, so if the degrees of freedom is 24, then the critical values are going to be plus or minus 0.388. So if I draw a little picture for this one, all right, so we've got negative 0.388, and then on the right side we've got a bound on that part of the rejection region is positive 0.388. And then I guess I've been making them red, might as well keep that going. So all right, so then there's a rejection region, and there's a rejection region. Okay, then where is our test statistic? Where is our sample correlation? It's negative 0.426, which is less than negative 0.388. So it's actually out here in that tail. So it's in the left tail, it's in the rejection region, right? So here you would reject the null, right? Because it's in that left piece of the rejection region. So R is in the rejection region. So the null should be rejected. And then the other part of this will also look exactly like example number 1. That we can say that R is significant since it is not between the positive and negative critical values. No, it's not, right? It's in the left tail. Therefore, it's past the lower one, so it's not between them, right? So just like before, it is significant because it is not between them. Just like with number 1. So whatever happens, really you only have 2 options. Either your sample correlation is in the rejection region, and in that case, it is significant since it's not between them, or it's not in the rejection region, in which case it's not significant because it is between them. So those are really the only 2 options that you can have as far as the conclusion goes. So as far as like of your 4 possible answers that you can pick, there are really only 2. Either it is significant because not between, or not significant because it is between. It's one of those. But that's basically how you do it. And I know I put a lot of extra introductory stuff in here and a lot of extra context, but it just, I don't know. It seemed weird to me to not put that in there. And it seemed like that made it harder to not have it. So I hope that does help, all the extra stuff I threw in leading up to these examples. Let's see. So then the next thing is linear regression. That's the best fit line. So like a regression line, that's the best fit line, like you do a best fit line to a scatter plot. And the general equation, and you'll see these hats. So like where there's the Y with the caret on top, like right there, that's usually pronounced Y hat. So the reason for the hat is to symbolize that that's a predicted Y value, not an actual one. That's all that the hat's supposed to mean, but that's why it's there. So that hat is on top of the Y to indicate that the regression line, if you use it for prediction, it will give you predicted values which don't have to match up with the actual values. It would be nice if they did, but you know, really it would be nice if they were close, right? You probably don't expect them to be perfect predictions, but if they were close, that would be nice. And then it's just a linear function, so mx plus b, where m's the slope, b's the y-intercept, right? Just like it is in algebra, or just like they are in algebra, since there are 2 quantities there. So one of the main purposes is to use it for prediction, and basically there you just substitute in. So for example, like it says there, for the furniture store data, if you go through and do it, then this is the line that you get. So this is what these tend to look like right here. And that's what they look like in the homework, where it's just y hat equals some number times x plus some other number, right? Where the slope is the number that's multiplied by x. So then the X variable there was advertising, and then Y was revenue. So then that regression model, which would be the right term for that, it's set up to predict revenue based on advertising. So like you could substitute in an amount for the advertising budget and see what the predicted revenue would be, right? That's what that model would do. So then, just for an example, what if 2.4 million was going to be spent on advertising? Because the amounts here were in millions, right? You can see in the table with the dollar MM, right? So, okay, you sub in the 2.4 for X. So you have 2.2 times 2.4 plus 1.5, right? So this, all you do is just sub in right there, right? So that 2.4 is just subbed in for X. And then you simplify it. So it's 2.2 times 2.4, and then plus 1.5, and you get 6.78, or $6.78 million. So altogether, what does that tell you? Well, from our model that we have, our model's telling us that if we have an advertising expenditure of $2.4 million, then the predicted revenue is $6.78 million. Doesn't have to match up with the actual, but that's the predicted revenue. And then notice here that the predicted revenues don't exactly match the observed revenues. Like none of them match exactly. So basically what I did to get this extra column in this table, because the original table just had the first 3 columns, didn't have this 4th one. All I did was, like, to get the 5.9, I subbed 2 into the equation for X. To get the 3.7, I subbed in 1. 8.1 subbed in 3, and to get the 10.3, I subbed in 4. That's all it was. And none of them match exactly. That's fine. The only way that they're all going to match up is if your original data set was perfectly linear, which in real life, you never get anything that clean, right? This is actually really, really good. Like these match up pretty well. Like you got an 8 and an 8.1. Those are real close. And so are the 10, the 10.3. I'd consider those to be really close. Maybe you can say, yeah, the 7 and the 5.9, those are a little off, right? And that's off by over $1 million, but this is still actually pretty linear. So the best fit line, generally, because the next thing is how do you get one of these lines, right? Like, how do you get this equation that's boxed in up here? Where does that come from? Well, what you want is you want a calculator or software to give you the line that fits the best, and that's the one that makes the predicted Y values closest to the actual ones in your data set. So in terms of what's best fit, it's what's going to fit your scatter plot the best, and that's what would be the best. So like all these little vertical distances, it's trying to minimize those generally, like rather than any one specific one, kind of doing it in aggregate, right? So to get it as close as you can for kind of all of them at once. All right, so mathematically, what you end up doing in order to get it, because there's this idea of least squares, the thing that gets squared is something called a residual or an error. And what a residual is, it's the difference between the observed and predicted Y values. So like in that example, the observed and predicted revenue. Symbolically, it uses an E, not an R, because R is already taken for correlation, so you can't reuse it. So you use the E that stands for error, right? And then the best fit line is the one that minimizes the sum of the squared residuals. And that's why you get the phrase least squares regression, or least squares regression line. That's where that comes from, because it minimizes the sum of squared residuals. And you can't use just the regular residuals, because for any data set, the residuals always add up to 0. And you can see them right here. If you added up those 4 numbers, you would get 0. Right? Those 3 on the bottom, if you add them together, you get negative 1.1. So then you add that to 1.1, yeah, that's 0. Because you always subtract in the same order. It's always observed minus predicted. And if you look, that's the way I did all those subtractions, right? 7 minus 5.9 is the positive 1.1. And then 3 minus 3.7 would give you the negative 0.7 and so forth. So it's kind of like with the standard deviation when we talked about that computation, where there, like in order to get the variance first, you had to have the deviation squared, because when you add up all the individual deviations, you always get 0 no matter what the data set is. It's kind of the same idea. When you add up the residuals, you always get 0. So the thing you end up minimizing involves the squares. Then let's see, this last thing before we get to the software, how to interpret the slope. That showed up once. I ran the homework like 4 times, I think. And there was one question where you didn't have to do it, but there was a reference to it. So I figured it was worth including. So what the slope of a regression line would tell you is it gives you the predicted change in y when x goes up by 1. And I know like in algebra, there are different ways of thinking about the slope, like rise over run and change in y over change in x. But when you're talking about regression, this is the way you want to think about it. If x goes up by 1, what does y hat do? So in the furniture example, the slope is 2.2, right? We got the equation of the line there again. So that would tell us that if you leave the context out, if x goes up by 1, predicted y, or y hat, goes up by 2.2. But then if you include the context, then the x variable was advertising expense. So if that goes up by $1 million, since here that's what 1 unit is, right? Since it's dollars in millions, so 1 unit's $1 million, then the predicted revenue, the y hat, would increase by 2.2 million, right? It's an increase because it's a positive slope. If you had a negative slope, then you'd have a decrease of some kind. All right, finally getting to using the software. So the Newton notes show you how to do it with a calculator, specifically a TI-83 or a TI-84 Plus. But what if you don't have one of those? Then you're not going to be using one, I would imagine. So there are a couple of options here that are free applets that'll work out fine. StatKey, which in my old job, that was the book that we used and it came with free software. That's its URL, and I made a video for that, and I'll post that in Moodle. I have an old video from like 3 years ago that I made for StatKey, and StatKey hasn't changed, so it would still work. The other one is this website for social science statistics. It's got a bunch of ads all over it, but also the data entry I think is a little bit simpler. So, I mean, I guess that's the trade-off. So I'm going to get that loaded really quick. I'm going to pause the video and do it, and then I can show you how to do this with the software, or with the applet, I guess. All right, now that I've got those ready to go in the other browser, so let's see then. There's StatKey, and if you're going to use that, if you want to try it out, I do have a video for it. Basically, you go to 2 quantitative variables, and then this is taking a while to load. Then you can see there's a scatter plot here, and then you just go to edit data, delete all the data in there, and put your data in there, more or less. But since I have a separate video for that one, I'm going to focus on this, which is the social science statistics one. So for the furniture example, and like with the advertising and the revenue, so the X values that we had, and I'm going to preserve the order. So you want to make sure you use the same order because the X and Y values for each individual need to match up. So I'm going to put them in exactly the same order, which would be like this. So it's 2, 1, 3, 4. And the Y values are 7, 3, 8, and 10. So then in the first rows in each, that's one individual, right? Those are going to match up. And then the 1 and the 3, that's the second individual. Because the first, and they're months, right? Like the first row is July, then August, then September, then October. So you want to put the numbers in the exact same order. You need those to match up. All right, so then if I go down here to calculate the regression equation, there it is, right? Y hat equals 2.2x plus 1.5. That's the exact same thing that we had, right? So let's see. I don't know if I can't draw when it's a live browser like this. It doesn't look like. So, all right, well, you can see it right there, the 2.2x plus 1.5. That's pretty much what you would have to do here. So let's see then. I think we got some more examples. So then this next example with the amount of damages from fires at middle-class residences in the city and the distance to the nearest fire station. So first thing is the regression line. So what I'm going to do, I'm going to go and I'm going to reset. So I guess I can go here and do it. I'm going to reset this. And then I'm going to put in the X values and the Y values exactly like they are here. So I'm going to just follow this order. When I put my X values in, it's going to be 5.2, 4.4, 3, in that order. Then the y values are going to follow that exact order as well. So if I go there and do it, so the x values are 5.2, 4.4, 3, 1.2, 7.5, and 9.3. And then the y values are 36.2, 28.9, 22.6, 8.8, 41.5, and 25.4. Okay, then if we go down and calculate the regression equation, there it is, right? You even get a nice little scatter plot here too. You get a bunch of other things down here that we don't really need for what we're trying to do. I mean, I guess down at the bottom you can see the regression equation again, but since it pops up right up at the top in bold, I would probably just take that one and go. Our book tends to write everything with, our book, like the Newton open source book, and the homework tends to use 3 significant figures for the slope and intercept, so I'm going to stick with that. So I guess then that means I'm going to say the slope is 2.48, and then the intercept would be 14.6. So, all right, then the regression equation, we're going to have that y hat is 2.48x plus 14.6. All right, and then part B is what's the predicted damage for a residence 6 miles from the nearest fire station. So really, if you took the context out, what this is asking is if x equals 6, what is y hat, right? Because damage, or predicted damage, that's y hat, right? And then this part right here is x equals 6, right? So that's pretty much what we've got going on here. And really what that means is you just sub 6 in for x and simplify it. So then you'd have that y hat is 2.48 times 6 plus 14.6. And what you end up with is 29.48. Or if you prefer this written in ones, because how this is written in thousands of dollars, like it says right up there. So I guess to have the answer in ones instead of thousands, if you want to do the conversion, I think for this sort of thing, that would really be your answer. But if you wanted to write it in ones, just if that makes it feel like it's more finished, I suppose it would be 29,480. Right? Just multiply by 1,000. So move the decimal point 3 places to the right. And that's pretty much it. Like if you're going to use the equation for prediction, you just sub in, right? Let's see. The next thing is things that are trouble. All right. So first thing that's trouble is extrapolating. If you're going to use the equation of a regression line for prediction, you want to keep the x values that you're substituting in to values that are within the range of x values in your original data set. So we just did it for 6 in this last example. And if you look at this, 6 is okay because the x values, like they go from 1.2 up to 9.3. Right? 6 is in between those, we're good. But if we wanted to know the predicted damage for a residence is 20 miles from the nearest fire station, our model doesn't really support that. Right? Because that's going way out there, and at that point we don't even know if it should be a linear pattern anymore. Right? Maybe at that point when it's that far away, maybe there's like some increase in slope or something that happens just due to other factors that would occur because you have to go 20 miles, right? Like that's pretty far for a fire truck to have to go. So you can't really go that far out there. And that's the idea with extrapolation. And this example is like really what this is it's the cost of gas. Or I guess really it's the cost of oil, right? Which you would then turn to gasoline. But it's like the cost of a barrel of oil, and it's all normalized to $2,005. So it's all inflation adjusted. So through the 70s, notice they're going upward, right? Like that's an upward trend clearly. And that's one of those things where if you think, well, yeah, like in the 70s, there was the gas shortage and, people were assigned specific days when they could go get gas during the week, right? Like, and that was going on, right? We just didn't have a whole lot of gasoline to go around, basically. Um, and I guess it wouldn't have helped that the fuel efficiency was significantly worse at the time, right? People were driving Oldsmobiles that were enormous cars, and maybe getting 10 or 11 miles to the gallon, right? Like a lot of cars were really big back then, really long. My parents had an Oldsmobile that could comfortably sit 6 adults. I'm not kidding. Um, so, I mean, I'm sure that factored in too, but as far as the shortage goes, but gas was expensive. And then if you try to extrapolate past this point, which is, so notice where this cuts off. This cuts off in 82. And, well, it really cuts off before that, because if you look at that point, that looks more like that point is actually 81. But really, this right here ends up being the peak, right? It doesn't keep going up. This is actually where it's starting to go back down. Because if you look at the other one, look where this starts. It starts in 1980, and then it's going downward. And then there's a little bump here for the Gulf War, right? I mean, like that's that time period, right around 1990. But like it goes way down. And if you extrapolated based off of the graph on the left, you would not end up with what actually happened. You wouldn't end up with anything that was remotely close to what actually happened. Your projections would just keep going up and up and up and up and up. So like for 1995, you would get this huge number, but really in 1995, gas was cheap. Like it, and even when you got closer to the millennium, it was even cheaper. And you can actually see that right here. That I remember. Like I remember gas when, and this would have been like maybe in 97 or so, being 89 cents. So yeah, like this, this matches my experience pretty well. Um, but then, I mean, that's the problem with extrapolating, right? You go past the range of your X values in your data, you don't really know what's going on out there, right? And this is kind of an extreme version of that, where what actually goes on out there is the exact opposite of the trend that was there in the 70s. But that's kind of why you don't want to do it, right? Like you don't really know. Like it could be something crazy. Like maybe it keeps following the same pattern, but maybe it doesn't. Maybe it does something totally different. So other things to watch out for, if you have something non-linear, which would be like this picture here on the left, right? A best fit line wouldn't fit that very well. It would be better with maybe something that did that, right? Like a best fit curve. So that's non-linear. Probably don't want to use linear regression there. The other thing is that if you have an outlier, it might really distort what the best fit line is, especially if your data set's not very big to begin with. So like if you have that outlier, like that red dot in the corner, if you ignore that for a second, just look at the blue ones. If you drew a best fit line through the blue ones, right, it's just, it's this upward trend that goes through them, right? Something like that. If you have that red dot in there, let me change colors for this one. Basically, it's going to go through this clump of blue, but toward that red dot. The line will get pulled toward it, because otherwise you're going to end up with a huge squared residual. So what will end up happening is you're going to get something that kind of goes like this. Actually, it's not so great. That's a little better. And it'll go right toward that, kind of like that. So that one point, that red dot, that outlier, if you leave that in with these other points, you're going to get a regression line with a negative slope that's somewhat steep. But then the green one, if you leave the outlier out, you get a positive slope that's, it's not very steep, but it's a positive slope, right? Like that one point causes a huge change in what the regression line is going to look like, whether you include that outlier or throw it out. And with outliers, it depends, right? Like it depends on the context entirely, whether you should throw an outlier out or not. Like sometimes you should leave it in, sometimes you should throw it out. It depends. But if you have an outlier, it makes your regression line go crazy. especially if your data set's not very big. All right, then the last thing is, and this kind of factors in extrapolation, this other example. So turbidity is basically cloudiness, right? So like more turbid water would be cloudier water. So that's what the bigger numbers would signify. And if you look at what the explanatory variable is, or your input variable, that makes sense, right? The more solids are in the water, then the cloudier it's going to be, right? And that's basically what you get out of this model. So we're going to predict the turbidity. So we're going to predict how cloudy it is based on the concentration of suspended solids. So first things first, we're going to get the regression line for predicting turbidity from suspended solids. All right, so let's see, I guess I need to clear that out. And then what we have is, so our x values, and again, I'm just going to follow the order they show up in. So it's in the table, it's 60, 61, 75, 100, and 90. And then the y values, the turbidity, 30, 25, 30, 45, and 41. And then compute, and there it is. So I guess, again, with the three significant figures, I guess I'm going to have 0.452 for the slope, and then negative 0.710 for the y-intercept. All right, so our regression line, it's going to be y hat is 0.452x minus 0.710. Right, that's what we got. All right, so then what's the predicted turbidity if the suspended solids concentration is 85? So then that's saying, right, if x is 85, what is y hat? Right? But we can figure this out, right? We just have to sub the 85 in for x, so y hat is going to be 0.452 times 85 minus 0.710, or I guess I can just write that as a 0.71, and what you get is 37.71. Then the other part is that reasonable? Well, the thing that you'd have to check is the 85 within the range of the x values? You go, 60, 61, 75, 190. Yeah, 80's within that, right? It's between 60 and 100, right? Like you look at the low one, you look at the high one, there's 60 and 100. 80's in between them. We're good, right? And that's basically the whole thing. So for that second part, brown. All right, so we can say that it is reasonable to make this prediction since 85 is within the range of the x values in the data set, which we just said was 60 to 100. Right? Low was 60, high was 100, 85's in there. All right, we're good. And then what about 50? Well, you kind of already know what's coming, right? 50 is not between 60 and 100. So this one's not going to be reasonable, but we can still do the prediction. It's just that the prediction isn't worth very much, right? Like you can still sub in the number and do the algebra. It's just that, what's that really worth when your suspended solids concentration is that low, right? It might not be a linear model anymore. So what we're trying to figure out now is if x is 50, what is y hat? Well, y hat would be 0.452 times 50 minus 0.71, which is 21.89. And then is it reasonable? No, because that's outside the range of the x values. So this time I'll say it is not reasonable since 50 is outside the range of the x values in the data set. So basically anything between 60 and 100 we're good, right? Since that's the range of the x values. But 50 is too small. If you wanted to do the prediction for something like a suspended solids concentration of 130, that's too big, right? Got to be between 60 and 100 or it's not really appropriate. Our homework is a real stickler on the extrapolation, and sometimes they'll give you questions that are really, really close to that range. And sometimes in practice, people do those. If it's, like if it was 60 to 100 and you did it for like 102 and did that prediction, that's probably going to be okay, right? But the homework is a stickler about it. So when you're doing the homework, you should be a stickler about it too and just be like, nope, 60 to 100, 102 is totally unacceptable. So that's not necessarily the way it goes in real life. I guess that's another context thing. But I guess when you don't know the context, because the homework problems sometimes don't have any, then actually you probably should be a stickler. All right, so then this would be extrapolation. I'm going to write that in. So then this prediction would be considered extrapolation. All right. That is everything for 3i. I know this is really long, but it kind of lends itself to that. So there's a lot there, but that's also why I postponed this one and postponed the quiz a little bit, or the test, the unit test, because there's a lot of stuff in 3i. It is not a normal length for one of these sections.